Hi, I'm Manos Caprichos from University of Michigan. This is joint work with my former student, Ramzi Janaksoy, who cannot be at SOSP because he and his wife are having a baby very soon. Now, unless you are a first-year graduate student or you happen to always attend the hallway track at SOSP, I would assume that you have heard of replication protocols before. Just in case you haven't, here's a very short summary. We have about 10,000 of these protocols. There are 3 flavors. There are a few primary backup protocols. We have a few thousand protocols named something Paxos. And then we have all these very complex protocols that you wish you could ignore, but blockchain technologies won't quite let you do that. Now, all these protocols are very different from each other, but they're all fundamentally solving the same problem. You have a service, you want to provide it to your clients 24/7, but you can't rely on a single server to do so. If that server fails, then your service will become unavailable. So instead, you replicate, you add more replicas, and more importantly, you make sure to keep those replicas consistent with each other so that even if some of them fail and go away, the client can seamlessly fail over to another replica and will not be able to tell the difference. And that's the ultimate goal of replication, to provide to the client the illusion that it is talking to a single correct server. Just a single machine that happens to always remain available. Now, while we were busy designing all these 10,000 protocols and building this beautiful illusion, in the real world, something very interesting happened. Our system started becoming more and more complicated and larger, to the point that some of these services that we're replicating are no longer standalone services, but they are part of a larger system and must thus interact with other components of that system. So, for example, if I send a request to Expedia, Expedia will receive my request, it will start processing it, but at some point, it will realize that it can't process the entire request on its own. It must interact with other parts of the system. For example, it may need to interact with an airline in the backend to actually book my flight, with the hotel to book my room, or with the bank to actually charge me for my transaction. So it will send a nested request to one of these services, or to all of them. It will wait back for the response to come back, and then it will finally keep executing the rest of my request and will send me the response. Now, the question is, in this setting where our services interact with other parts of the system, can I use our existing replication protocols out of the box? Now, initially, the answer may seem to be, sure, why not? Just add the number of replicas, then choose your favorite replication protocol, and you should be just fine. After all, for 30 years, we have strived to provide this illusion of a single correct server. And if I have a single correct server, then why can't my single correct server interact with other parts of the system, send nested requests, and do whatever it wants? Except that's not exactly what is happening here. Because for 30 years, we have strived to provide the illusion of a single correct server to the client only. Because the client was the only entity in our system that was observing any kind of output from our systems. So internally, our protocols were allowed to use any kind of crazy optimization that they wanted. Anything like Byzantine fault-tolerant, multi-threaded speculative execution, which could produce any number of inconsistent results. And it was all fine as long as the client was shielded from all that ugliness, and all that it saw was this beautiful illusion of a single correct server. But in a world where we are exposing our intermediate states through our nested requests to other parts of the system, it becomes very important that we maintain this illusion. We currently shatter that illusion. We keep it towards the client, but we shatter it towards any other service that is exposed to these intermediate states through our nested requests. So, this is what this talk is about. Try to identify the impact of all these interactions on the design of our replication protocols, and where possible, to try to mitigate them by providing solutions to all these problems. So, in this talk, I will try to give you concrete examples of how these interactions of our services with other parts of the system can affect both the correctness and the performance of our replication protocols. I will provide some solutions for these problems, and then I will try to quantify the benefit of those solutions. Now, in the paper, we talk about 3 different classes of correctness problems. In this talk, I will only have time to talk about one of them, which is how does using speculation in our protocols, how can that affect the correctness of our replication protocols? So let's get right to the first problem. I will use the example of primary backup. This is one of the simplest replication protocols that we have. The way it works is the following. Clients would send requests to the primary receives those requests, executes them, and then sends the a state update to the backup to make sure that it also has that new state. It waits for an acknowledgement back from the backup, and then it sends the response back to the clients. Now, notice that the primary is careful to only send the output to the client after it has been properly replicated on both replicas, so it can survive the failure of the primary. Now, this protocol works perfectly fine in the client-server model, but what if I move on to an example like the Expedia from before, and I try to apply this primary backup protocol out of the box in this new setting? So let's see how this would work. Let's say I send a request to Expedia. I want to book a flight. Now I send it to the primary. The primary normally executes my request. Part of the execution is that it needs to send a nested request to the bank to actually charge me $500 for my flight. So it does that, and before it has a chance to do anything else, the primary dies. Now, at that point, according to the primary backup protocol, the backup will become the new primary, and it would start executing requests just fine. Except in this case, it's not just fine, because at this point we have left our system in an inconsistent state. The backup, the Expedia service, has no idea that I ever made a request to book a flight, but the bank has already charged me $500 for that flight. Now, this inconsistency arises precisely because there is a double standard here. We treat our output commits to the client with extreme caution, making sure to have replicated everything properly before we expose any kind of state to the client, but there is no such check for all the states that we're sending towards backend services. So, if there is one lesson that I would like you to take away from this talk, is that it was written in the constitution of state machine replication that all output commits are created equal. So, if you are designing a protocol and you're making an output commit towards any external entity, you need to treat those output commits with the same reverence that you are treating your output commits towards the client. Now, this does not mean that you have to give up techniques like speculative execution. These are very useful for performance. As we show in the paper, you can still use speculation within your services as long as you make sure to contain the effects of speculation within the service itself. What this means is that you need to resolve the speculation before making any kind of output commit. For example, before sending any nested request to another service. Now, this should not even be a surprising revelation. This is the principle of rethink the sync from all these years ago, except now applied at a very different context, that of speculative replication protocols. So now let me move on from correctness to also show you how these interactions with other parts of our system can further hurt the performance of our protocols, not just their correctness. In particular, I will focus on the case of sequential execution, which is the default mode of execution for all the protocols like Paxos and almost all the variants of Paxos. So, just a very quick recap of how Paxos works. We have clients that send a request to the primary. The primary receives the request and then decides what order will execute these requests. So let's say proposes to execute B first and then A, and then runs the Paxos protocol so that all replicas agree that we should execute first B, then A, then C, and whatever other request is coming after that. So, after we agree on the order, the replicas have a very simple task. Execute the request sequentially in the order that was agreed upon by the Paxos protocol, and this will make sure that all the replicas will arrive at the same states. Now, in the client-server model, this again works perfectly. However, this sequential execution in a world where services interact with other services can be actually harmful for performance. Let's see how this, let's say we have 3 requests, and let's see how this request will be executed by a Paxos protocol. Let's say they have request 1, 2, and 3, and I start executing request 1. At some point, I get to the point of the execution where I need to send a nested request. So, I send a nested request, and wait, there is nothing else that I can do. while that request is in flight, I cannot keep executing the rest of the request because I need the result to come back. I cannot keep executing any other request because I am bound by sequential execution, which results in my service spending a lot of time just remaining idle, waiting for all these nested requests to come back from other services. Now, the good news is that once you realize what the problem is, it turns out the solution is not too complicated. The real problem is that we're using sequential execution as an easy way of making sure that all the replicas will arrive at the same state, but we don't fundamentally need sequential execution here. All we need is just any deterministic execution schedule across these requests. So we propose a very simple alternative where instead of sequential executing requests and having to remain idle while the nested requests are in flight, we will execute them in what we call request pipelining mode, which is just execute them. If the request at some point blocks, you switch to the next one in a round-robin deterministic manner. So let's see the example with these 3 requests. Let's say I start executing the first request. If at some point it blocks, waiting for a nested reply, a nested response to come back, we don't have to actually block and remain idle. We'll just move on to the execution of the next request. If that one blocks, then we will move on to the third. If that one blocks, back to the first one, and so on. Now, this has the benefit of providing determinism across all replicas without having to wait while our nested requests are in flight. However, it does have a very weird feature, which is that I'm no longer executing these requests atomically, which means this is no longer a linearizable execution. Now, I know that many of you may have been conditioned by reading 1,000 papers on Paxos and BFT protocols to think that all replication protocols should provide linearizability. But if you think about it, that is not actually true. It is not the job of the replication protocol to enforce linearizability. I will say this again. It is not the job of the replication protocol to enforce linearizability. Its only job is to make sure that the replicated service is indistinguishable from a single correct server. If that single correct server wants to have some weaker property of consistency, like it wants to execute requests in parallel without acquiring any logs because that gives it higher performance, then if I replicate that service, there is no reason for me to enforce something stronger and thus lose all that performance. On the other hand, if the application does want linearizability, then it can enforce it end-to-end by simply acquiring the appropriate logs on its requests. Now, I understand that's a lot to process, so in the meantime, let me switch on to just briefly show you the evaluation of Aegean to quantify the performance benefits of the techniques that we propose in the paper. And keep in mind that the contribution is, I guess the performance benefit is just half of the contribution, the other half is ensuring correctness in this context. So the setup of our experiment is pretty simple. We have clients, they're sending requests to a middle service, which then makes nested requests to a backend service, and every request incurs a total of 1 millisecond of execution time on each of these services. So on this graph, I will plot, on the left is the throughput of the unmodified Paxos protocol, which is using sequential execution, and on the right, we have the modified version that we use in Aegean, which is similar, except now it uses request pipelining. So it doesn't have to remain idle while the nested requests are in flight. You can see that even the simple optimization gives us more than 2x benefit in terms of throughput. But this is not where the throughput benefit ends. This is, if you want, the direct part of the throughput benefit. Aegean can also indirectly improve the performance by ensuring that techniques like speculative execution can be used safely in this environment. This means that I can start thinking of using protocols like Eve. Eve, if you remember, is a protocol for replicating multi-threaded services, which uses speculation internally. So while Eve was perfectly fine in the client-server protocol, if I try to apply it out of the box to this new setting, it is not safe because of speculation. So instead, we modified Eve, and we built a version of it that takes into account all the lessons of Aegean. And it turns out that that version is not only safe in this new setting, but it's actually twice as fast as the original Eve protocol. Because apparently, I didn't actually tell you the whole truth about request pipelining. Request pipelining doesn't only improve sequential executions, it actually gives you a performance benefit anytime, even in a multi-threaded execution, as long as your requests block while their nested requests are in flight, request pipelining can still help you. So, in this talk, I argue that the simple client-server model is not always appropriate these days, as our services may interact with other components of the system. In the presence of such interactions, we need to rethink the design of our application protocols, both to ensure that they remain correct and to optimize their performance. Thank you very much, and let me know if you have any questions.
Hi, so I'm Chinmay from Utah. I really liked your talk. I've got a question about your request pipelining. It seems that Zookeeper also supports something like this in the form of alpha linearizability or asynchronous linearizability. I don't understand that quite well, so I wanted to know how this compares to that. It seems that it also allows you to implement your application in a similar manner.
So this is not, I would say that this is not about the performance, the consistency property that you provide. Okay. This is about the mode in which you would execute, which again doesn't have to be about whether you want linearizability or not. You can even do linearizability in this setting by just enforcing stronger locks and perhaps losing some of the performance involved here. But it's a mode of, basically, the bigger point here, which Zookeeper doesn't do because they are not in this setting at all, is to not remain idle while your requests are in flight and just start executing other requests while my request is in flight for the first one, I will just execute the second request. But you need to do it in a deterministic way across all replicas. By the way, Zookeeper also doesn't have this active replication, so it's not exactly, that's not exactly the mode of execution. It would be a very different setting to implement that in Zookeeper.
Okay, thank you.
Hi, Matthew Milano, Cornell. I have another question about consistency. It strikes me that normally when you weaken consistency in a system, you do so that you can let your replicas get out of sync. I'm wondering what opportunity there is to say in Aegean, we're expecting that a single server that can tolerate operation reordering can get a performance benefit. If it can tolerate operation reordering, can it also tolerate, say, replicas lagging behind?
So you can tolerate replicas being out of sync to some degree, right? The point where you can no longer tolerate it is the moment they make any output commit. In the original model to the client, in this model to any external service. Right? So you can be, again, you can allow your replicas to run wild as much as you want, as long as when it really matters, during the output commit, they present this illusion of a single correct server. Right? And this is how we get most of the performance with protocols like Eve or all these protocols, the original primary backup protocol. That's how you get a lot of your performance by you don't have all your replicas be in a full lockstep all the time. You allow some freedom for performance, but then you want to make sure that that freedom doesn't affect this illusion of a single correct server the moment you make your output commit.
That makes sense.
Hi, John Howell, VMware Research. I like this system a lot. It seems like a lot of the complexity you're observing comes from the modeling the call to the backend as an RPC. But if instead...
Sorry, how was that again?
It comes from modeling the call from the backed up service to the backend as a round trip, as an RPC. If instead of a call out, if you thought of it, if you modeled every step in that system as a one-way message send, then messages going into the replicated service are treated as a call to the replicated service, and outbound messages are just stored in a buffer, and you have to call in to get them. Then at that point, your dictum that all output commit, every output commit is equally valuable, I think sort of solves the problem on both sides for both the clients and the backend, and you can kind of derive this result directly by just treating these as one-way message sends.
So in theory, I think you could do what you're saying. You're saying basically treats everything as a full message passing, and I just execute half of my request. If I need to send a nested request, that's just a new request. So imagine how you write a program for that, for your code. I have execute them somewhere deep in my stack, and I want to make a nested request, and then at that point I need to save the entire state, store it somewhere, make a different request, And when that request the response to that request comes back, I need to make sure that I remember that this is actually matching to that request, then restore all my state, and then keep executing that second half of the request as a separate request. You could do that, and you're allowed to do that if you want. Most people would like to just do an RPC to the backend service.
Fair enough.
I think John is referring to the fact we tried this technique in Farsight, and it worked out pretty well. But to your point, a lot of people actually do like to use RPCs rather than message passing. So your point is valid. All right, let's thank the speaker.